Alright, so we're going to talk about the types of variables here. So we have, first one's called a discrete variable. And a discrete variable is a random variable that takes on only a countable number of distinct values such as 1, 2s, and 3s. These usually involve any type of counting. So just think of it this way. A discrete variable cannot be a fraction or a decimal. You can only have whole numbers. Okay, so for instance, if you're rolling a dice, you can get a 1, a 2, a 3, a 4, a 5, or a 6. Those are discrete, but you cannot get a 1.5. Okay, so that's a discrete variable. And then a continuous variable is a random variable that takes on an infinite number of possible values. These usually involve any types of measurement. Okay, so if we were measuring people, they could be 60 inches, they could be 61 inches, they could be 60 and a quarter, they could be 60.67. Okay, so basically with these you have no fractions or decimals. And these you can have fractions or decimals. Okay, so that's basically the way that you can look at the types of variables you have. So a normal model, for instance, is continuous. Okay, so when we look at a typical normal model, we could have anything on that continuum from whatever we're looking at. Okay, because we take on all values. Okay, whatever the mean is, but then you got the standard deviations going left and right. So that would be an example of a continuous variable. Okay. All right, so let's look at this game here. Now this is a game where we can win. We get a 1, 2, or 3. We get 0. We get 5 points for a 4 or 5, or 50 points for a 6. So this would be a discrete variable. Why? Because we can only win 0, 5, or 50. So we can't win 2.5 by playing the game. We can only win those 3 values. So those are discrete. And the probability of each of those is this is 3/6, and this is 2/6, and this is 1/6. Now the expected value is simply all we're going to do with the outcomes and the probability is we're going to multiply them. Okay, so this would be 0, this would be 10/6, and this would be 50/6. Now our expected outcome is simply the sum of each value x, these are your x's up here, those are called the outcomes, times its probability. And this is p here. So we already did x times p, that's these. This means to add them. So we would do 0 plus 10/6 plus 50/6. We would get 66, which is 10. Now you're going to say, hold on, you can't win 10 by playing this game, and you're absolutely right. You can win 0, 5, or 50. What that 10 represents is that's the expected value if you were to continue to play this game. So most of the time you would win 0, sometimes you would win 5, and every so often you would win 50. Okay, so if you were to play the game, just think of it, for every 6 times you play the game, you would expect to win 0 3 times, you'd expect to win $5 twice, and you would expect to win $50 or 50 points once. Well, if you took that average, you did 0, 0, 0, 5, 5, you'd get 60 divided by, you played the game 6 times, so every 6 times you would expect to win 60 points. And that comes out to 10. So what is that then? Well, that's the mean. That's mu. Okay, so for every 6 times you play the game, you would expect to win 10 points. Now this whole standard deviation thing, I just want to go back. And if you guys remember, I think it was back in chapter 6 where we calculated a standard deviation, and I told you really didn't. I wasn't going to ask you to do it, but you do got to keep the formula in the back of your mind. The first thing that we did is we calculated something called the variance, right? And the standard deviation is the square root of the variance. Well, how do we calculate the variance? We took each value and we subtracted from the mean and we squared it. Okay, and then we added all those together, so that was a summation, and then we divided by n minus 1. And that was because we were doing a sample standard deviation. And then all the standard deviation was the square root of the variance. Okay. So the whole point was the deviations that we were looking for were the deviations from the mean. Okay, so we took each value, found the deviation from the mean. Some were positive, some were negative, so we squared them to make them positive. Added up all those squares, and because we squared them to get back to the standard deviation, we then have to do the square root. So what we're going to do with this variance is we have kind of another variable here, but we're going to take the sum of each value minus the mean squared. So we're going to make all those deviations positive, but then we got to multiply each of those by its probability. So what are each of the outcomes? Well, those are here. And what's the mean? Well, that's the 10. And what's the probability? That's this thing right here. So here's what we're going to do. We got to do the sum of 0 minus 10 quantity squared times 3/6. And then we have to do 5 minus 10 quantity squared times 2/6. And then we have to do 50 minus 10 quantity squared times 1/6. So this is 100 times 3/6. This is 5 minus 10 is negative 5 squared is 25 times 2/6. And that's 40 squared is 1600 times 1/6. So this becomes 300/6. This becomes 50/6. And this becomes 1600/6. So if we add all those together, we get 1950 over 6. And if we do that out, we get 325. That's the variance. Now to get the standard deviation, we simply do the square root of that. And we get 18.03. Now, that's the standard deviation. That's the based upon this average if you kept on playing the game. Okay, if you kept on playing the game. Okay. So, this is on your AP formula sheet. You don't have to memorize that. And this is on your AP formula sheet, so you don't got to memorize that. So we just got to know how to use it. Okay. Now remember, this is the formula for the variance. Biggest mistake I see students making is they get this answer, they circle it, and they say, oh, that's the standard deviation. No, it's not. That's the variance. That's how much each one varies from the mean. But because you squared everything here, You know, we squared. You got to unsquare it to get the standard deviation by taking the square root. So now we double the points. Okay. So if we double 0, we get 0. If we double 5, we get 10. If we double 50, we get 100. Probabilities do not change. So we get 0, we get 26ths, and we get 106ths. To get the expected values, we do the sum of each outcome times its probability. We've already done those, and then we add them. So 0 plus 26 plus 106 is 126, which is 20, which is mu. Well, there's a surprise. The original mu was 10. We doubled the points. The new mu is 20. Okay. So remember, doubling means you multiply by 2. So if you remember back in the first unit, you know, we talked about that multiplication, if you remember, affects everything. Measures of position, measures of center, and measures of variation. Addition only affects measures of position and center, but not measures of variation. So in this case, we're multiplying. So our new variance is we're going to do the sum of each value minus the mean squared times its probability. So the first one, outcome is 0 minus 20 squared times 3/6 plus 10 minus 20 quantity squared times 2/6 plus 100 minus 20 squared times 1/6. So negative 20 squared is 400. So that's 400 times 3/6. 10 minus 20 is 10. Negative 10 squared is 100 times 2/6. And 80 squared is 6,400 times 1/6. So this becomes 1,200 sixths, 200 sixths, and 6,400 sixths. So if I add those together, I get, let's see, that's going to be 7,800 over 6. And if I do 7,800 divided by 6, I get 1,300. Now our original variance was 325. So what is this? Well, this is 4 times that. Okay, but when we do the standard deviation, take the square root of that. We get 36.06. So look what happened. The standard deviation was 18.03. The new standard deviation is 36.06. Okay, so the standard deviation doubled. Okay, so the reason this is 4 times that is, remember, you got to do the square root. The square root, if you were to put a 4, in order to double this, if I want 325 to double, I got to multiply it by 4, because what happens is that square root takes out that 4 and makes it a 2 when I take it out of the square root. So in order to make this double, I would have to multiply that original value by 4. That's why this is 4 times that, what that is. But again, we expected this to happen because when we multiply, measures of variation also change. So the standard deviation doubled. Okay. So now we're playing the game twice. So what are our outcomes? Well, we can win 0. Let's say we can win 0 and 0. So that would be an outcome of 0. We can win 0 and 5 or 5 and 0. So that's $5. We can win 5 and 5, and that would be 10. Let's see, we can win let's see, 50 and 0, or 0 and 50. Or we can win 50 and 5. Okay, so let's see what we have here. Let's see when so 0 and 0 would mean we got one, let's see, 3/6 times 3/6. So that would be 9/36. Now 5 would be 0 and 5 or 5 and 0. So that would be 3/6 times 2/6. But there's two ways I could do that. I could do 0, it's an OR. Think of it as an OR. So I really got to add it. I can do it either way, 0 and 5 or 5 and 0. So I'd have to multiply that by 2. So that would be 6. That would be 12/36. 5 and 5, there's only one way I could do that. That would be 2/6 times 2/6, and that's 4/36. 50, I could do 0 and 50, or 50 and 0. So that would be 1/6 times 3/6. But I would have to double that because I could do 0 and 50 or 50 and 0. And that's 3, that's 6/36. 50 and 5, I could do 50 and 5 or 5 and 50. So that would be 2/6 times 1/6. And I would double that. So that's 2/36, 4/36. And the last thing I could do is win 100. And that would be 50 and 50, and that would be 1/6 times 1/6, and that's 1/36. So let's see what happens. We got 9/36, 12/36, so that's 21/36. Plus 4 is 25/36. So we're 25. We add 6, 31/36. We add 4. That's 35/36, and we add 1, that's 36/36, so it adds up to 1. We're good to go. So now I multiply. 0 times 9/36 is 0. 5 times 12/36 is 60/36. 10 times 4/36 is 40/36. 50 times 6 is 300. 55 times 4 is 220, and 100 times 1 is 100. So what's our expected value? Well, we add them up. 60 plus 40 is 100. Plus 300 is 400. Plus 100 is 500. Plus 220 is 720. So our expected value winds up being 720 over 36, which is 20. Well, holy cow. If you play the game once on average, you expect to win $10. If you play the game twice on average, you expect to win $20. Well, that's nothing new, right? So now we got to do this whole thing here where we do the variance. We do each value minus the mean. square it and multiply it times the probability. So we do 0 minus 20 squared times 9/36, and then we do 5 minus 20 squared times 12/36, and we do 10 minus 20 quantity squared times 4/36, and we do 50 minus 20 squared times 6/36, and we do 55 minus 20 squared times 4/36 plus 100 minus 20 squared times 1/36. So this is 400 times 9/36. 15 squared, I believe, is 225. Yeah, 225 times 12/36. This is 100 times 4/36. 30 squared is 900 times 6/36. What's that? That's going to be 35 squared. 35 squared is 1225 times 4/36. And then this becomes 80 squared, which is 6400 times 1/36. So what do we wind up with here? This becomes 400 times 9 is 3600 over 36. 225 times 12 is 2700 over 36. 100 times 4 is 400 over 36. 900 times 6, that's my phone in the background. 5400 over 36. 1225 times 4 is 4900 over 36, and then 6400 over 36. So if we add all those together, we get, what do we got now? We got 3600 plus 2200, 2700 plus 400 plus 5400 plus 4900 plus 6400. So it's 23,400 over 36. And if we do that, we get 650. Well, what happened is the variance doubled. Okay, so if we play the game twice, the variance doubled. Now be careful. If I take the square root of 650, I get 25.5. Now, that doesn't mean the standard deviation doubled. Standard deviation is 18.03. This is not twice the standard deviation. This is twice the original variance. Okay? So, what is the whole deal? The new expected value is simply, what are we going to do? Well, we're simply going to just add the expected value. So it's simply e sub x1 plus x2 is simply just add the means. So I get the new mean of game 1 plus game 2. But the new standard deviation, what do? I take the variance and I add the variances. So the standard deviation, this is really this is x and this is x, and this should be mu of x and mu of x, x plus x, because I'm playing the game twice. The new standard deviation from playing the game twice, x plus x, is the sum of the variances. It's the variance. So this is also known as the Pythagorean theorem. Of statistics. Why? Because what are you doing? Well, think of it as the legs of the triangle. If this is the variance and this is the variance, that's the leg and that's the leg. How do you get the hypotenuse? Well, you square them. You do a squared. Actually, let's think of it this way. These are the standard deviations. Standard deviations, what do? I square them. Well, what happens when I square them? What do I get? I get the variance. So that's variance plus variance. And then what did you do? You take the square root. Okay, so what are you doing here? You're adding the variances. That's the whole point. So if I play a game more than once, I don't add the standard deviations, I add the variances. Well, how do I get the variances? I square the standard deviations. It's the opposite of when you went from variance to standard deviation. You took the square root. Well, to go from here back to there, you got to square it. Alright, so the question then becomes, how do you know when to simply multiply the standard deviation by a fixed amount and when to add the variances? And the answer to that is, how many times are you playing the game? Okay, so if you're playing the game once and you're changing the outcomes, then you multiply. Okay. If you are playing the game more than once, then what do you got to do? Well, those are independent events. Each time you play the game is an independent event. So then what you must do in that case is you must add the variances to get the new standard deviation. Okay, so you add the variances. So what you do is, if I'm playing the game, let's say that I want to know the standard deviation. If I'm playing the game 3 times, x plus x plus x, then I have to add the variance 3 times. That's standard deviation squared, standard deviation squared, standard deviation squared. And that gives me the sum of the variances, and then I simply take the square root. As opposed to up here, if you play the game once, you simply multiply whatever number it is, however you're changing the outcome, times the standard deviation. And that gives you the new standard deviation. Alright, so we got a game where 2 cards are drawn from a deck, one after another. The game costs $1 to play. The player pulls a face card, they win $1. If the player draws 2 face cards, they win $5. So we are doing this as if we're running this game. So we're taking the $1 in and we're paying the $1 to $5 out. So we have 3 different outcomes, right? The person can give us $1 and win nothing, and we win $1. That's our $1. We're running the game. They can give us $1 and win $1, or they could give us $1 and win $5, which for us would be a -4. We lost $4. So the probability of each of these, this would be non-face card and non-face card. So there are 40 non-face cards in the deck. Face cards are jacks, queens, and kings. There's 4 of each of those. There's 52 cards. We took one out, we'd have 39 out of 52. Now this one here, they can win a face card, so it would be 12 out of 52 times, then non-a-face card would be 40 out of 51, or means we add, they do non-face card and then a face card. And this one here would be face card and face card, so they do 12 out of 52 times 11 out of 51. So if you multiply these, let me just put this over here. X, probability of X. You would get, let's see, we have $1, we have 0, we have -4, we have 0.59, we have 0.36, and we have 0.05. So for me to do the outcomes, I would get 0.59, 0, and -0.2. So my expected value is going to be these 3 added together, and it would be 0.39, which, by the way, is our mean. So on average, we'll win 39 cents if we're running this game. Okay, on average. Now the standard deviation, remember the variance is simply the sum of each value minus the mean squared times its probability. So we're going to do 0.59 minus 0.39 squared, and that probability is, I'm sorry, that's wrong. It's $1. It's 1, and the probability is 0.59. So the outcome is $1. We win $1. And then the second thing that can happen is we win nothing. Times the probability of that is 0.36. And then the last one is we lose $4. The probability of that is 0.05. Okay, so we put that in the calculator, just the way that is. Alright, what's going on here? So -4 minus 0.39 squared times 0.05. So that's our variance. It's 1.2379. Alright, and then our standard deviation would equal the square root of that. So if we take the square root of that, we get $1.11. Okay. So our variance here is $1.11. So if we have 100 people play, we would find the mean and the standard deviation. Well, what would our new mean be? Well, our new mean would simply be a mean of 100 different people playing would be 100 times 0.39. So on average, if we had 100 people play, we'd expect to win $39 for the night. Now, 100 different people playing the game, what would our new standard deviation be? Well, these are 100 different independent games. Okay, so each person is another independent event. So what do? Well, we would add the variance 100 times. Well, what's the variance? We know that the variance is $1.24. We got that right here. It's right there. So we would do $1.24. We'd add it 100 times. So we're going to do 100 times $1.24, and that's going to give us our new variance. And then we got to do the square root of that. So 100 times 1.24 is 124. If we take the square root of that, we would take, you get $11.14. So what's the probability that they make money? Well, we have a mean and we have a standard deviation, so we would want to get a z-score. Now, think of it this way. Here's our mean. Our mean is $39. For us to make money, we have to be right of 0. So we make money in this entire region here. Okay, so we got to get a z-score for this. So let's see what happens. Let's go into our, actually I don't even know if we need a z-score. What's the lower bound? Well, the lower bound is 0. What's the upper bound? The upper bound is can be as high as we want, so we can make $100 on the night. Our mean is 39. Our standard deviation is $11.14. So the probability that we're going to make money is pretty high, like 0.9998. 0.9998. Alright, so problem 5 here. We have Louis manages a golf course for a living. Louis gets a base salary of $1,000 a week. When business is really good, Louis gets a bonus of $500 a week. Probability he will get his weekly bonus is 0.2. Louis hires a part-time helper named Mikey to work for him 75% of the time. Mikey makes $200 a week, the other $25. When the course gets really busy, he makes $300. Okay, so we got to find the expected value for Louis. So Louis can make $1,000 or he can make $1,500. 80% of the time he makes $1,000. 20% of the time he makes $1,500. So this is 800 and this is 300. So 800 plus 300 is 1,100. So on average he'll make $1,100. The variance, we simply do the sum of each value minus the mean squared. So we do 1,000 minus 1,100 squared times 0.8 plus 1,500 minus 1,100 squared times 0.2. Okay, so that becomes 100 squared times 0.8 plus 400 squared times 0.2. That comes out to 40,000. And then we take the square root of that, and that comes out to $200. Okay. Which is the square root of 40,000. Okay, Mikey, he can make 200 or 300. He makes this 75% of the time, and this 25%. This is 150. This is 75. So that's 225. So the variance is 200 minus 225 squared times 0.75 plus 300 minus 225 quantity squared times 0.25. So let's see what that comes out to. And this is 300. And that's 1,336,000. Doesn't seem right, does it? Let's try it this way. 25 squared times 0.75 plus, what's that going to be? 75 squared. 75 squared times 0.25. That seems more reasonable. 1875 and 1875, take the square root. $43.30. Okay. So now what happens if Louis pays Mikey out of pocket? So Louis makes 1,000 and he pays Mikey 300. So that would be $700, right? Or you can make 1,000, so this would be 1,000 minus 300. This would be 1,000 minus 200. Or he could make his 1,500 and pay 300, and that would be 1,200. Or he can make his 1,500 and pay Mikey 200, which he goes home with 1,300. So the probabilities here are, this is and, so he makes 1,000 and he pays 300, so we're going to multiply here. So this is 0.8 times 0.25, so that's 0.2. This is 0.8 times 0.75, so that's 0.6, and this is 0.2 times 0.25, so that's 0.05, and this is 0.2 times 0.75, so that's 0.15. Okay, and then we multiply, so 700 times 0.2 is 140, 800 times 0.6 is 480, 1200 times 0.05 is 60, and 1300 times 0.15 is, I believe, 195. Well, let me just check. Yep, 195. So now we add all those and we get 140 plus 480 plus 60 plus 195, and we get 875. Okay. Well, Mikey on average makes, or Louis makes 1,100. Mikey on average makes 225. So how do we get 875? Well, we did 1,100 minus the 225. So this is really, all this really is this is the mean for Louis minus the mean for Mikey. So all we did is subtract there. Okay. Now the variance, we have to do each value minus the mean squared times its probability. So we have to do 4 of these. So I'm just going to do this kind of quickly. So this is negative 175, right? So that's 175 squared times 0.2. That's going to be 75 squared times 0.6. That's going to be 325 squared times 0.05. And that's going to be 425. Yeah, 425 squared times 0.15. And that's 41,875. Well, where did that come from? Well, the variance for Louis was 40,000. The variance for Mikey was 1,875. So what did we wind up doing? We wound up doing what? Addition. However, we were actually subtracting, right? But we still added the variances. Okay, we still added the variances. Okay, so the new standard deviation is just a square root of that. And that's 204.63. Okay, so how do we calculate the expected value of Louis minus the expected value of Mikey? The expected value of Louis minus Mikey equals the expected value of Louis minus the expected value of Mikey, which is really the mean of Louis minus the mean of Mikey. And we talked about that, right? We said, oh, where did this 875 come from? Well, all we did is we took the 1100 and we subtracted the 225. However, when we do the standard deviation, the standard deviation of Louis minus Mikey equals the variance for Louis, the variance for Mikey. We didn't subtract them, we added them, and then we took the square root. So we still add the variances. Add the variances. Variances always add. Variances always add. Okay? So our rule, when we subtract independent events, the expected value of x minus y equals e sub x minus e sub y. The new standard deviation of x minus y is the variance of x plus the variance of y. Okay, and then we take the square root. Okay, so what we wind up doing either way is we wind up doing the sum of the variances. Okay, sum of the variances, even when we're subtracting. Alright, so let's look at problem 6 here. So now we're just given, we got two events, and event A has a mean and a standard deviation, event B has a mean and a standard deviation. So 2A means I'm doubling A. So my new mean would be 2 times my original mean. And my new standard deviation would be, since I'm doubling it, I would just double my standard deviation. Now, they told us that these are independent events. So, when I add two independent events, I add the means. But when I add two independent events, I add the variances. So I get my new standard deviation. I gotta do 5 squared plus 3 squared, and then take the square root of that. So that is going to be 34, the square root of 34. And that's that's going to be 5.83. Now this is minus, so I do B minus A. So my mean would be the mean of B minus mean of A. But when I subtract, what do I do to get the standard deviation? I add the variances, just like I did right here. You're going to get the exact same thing. You might say, well, Mr. O'Neill, I got to add B, but it doesn't matter what order you add it. And if you do 3 squared plus 5 squared, you still get 36, and you got to take the square root. Now, when you're multiplying and adding, you do multiplication first and then addition. So we would do, for the mean, 2 times 50 plus 3 times 60, and that's 280. Now to do the standard deviations, I have to do 2 steps. So the first thing I have to do is I got to multiply the standard deviations. So I'm actually going to add 10 plus 6, but then since I'm adding, I got to add the variances. So the variance would be, I would wind up doing 10 squared plus 6 squared, and then taking the square root, whatever the square root of 136 is. It's 11.7. And the same thing when I do 5b minus 2a. I wind up doing 5 times 60 minus 2 times 50. And that's going to be 300 minus 100 is 200. And then when I do the standard deviation, the first thing I do is I multiply, so I do 5 times 3 is 15, and then 2 times 5 is 10, and I square those and I add them. Even though I'm subtracting, I add the variances. So it's 15 squared plus 10 squared. And it's square root of 325, and that comes out to 18.03. Alright, so we're looking at how to do these on a calculator. Okay, so you go to a party where Louis runs a game that costs $5 to play. To play, a player draws a card from the standard deck. If the ace of hearts is drawn, the person wins $100. For any other ace, the player wins $10, and for any other heart, the player wins $5. Any other card drawn is a loss. Is this a fair game? Would you be willing to play? Okay, so let's see. We can lose $5. We lose $5. We can break even. We can win $5, or we can win $95 because it costs us $5 to play. So here we paid 5 and won nothing. Here we paid 5 and won 5. Here we paid 5 and won 10. Here we paid 5 and 195. So this one is 1 out of 52 because there's only one ace of hearts. Any other ace, so there's 4 aces, so that must mean there's 3 more. Okay. Any other heart, well, there's 1 heart gone, so there's 13 hearts in a deck, so that means there's that. Okay. So if I add these up, that gives me 15, 16, so that must mean there's 36 left. Okay. Now, when I do an expected value and I use a calculator, I still have to show my work, so I'll show you how I do this. I say, okay, AP people, here's what I'm doing. I'm doing the first value, and I'm adding all these up to the last value. So you kind of showed your work there. Now, I'll show you how to put these in the calculator. Go to your calculator, stat, edit, and clear out list 2, 1, and 2. Clear out all my lists. And here are my outcomes. In the first list I do -5, 0, 5, and 95. Okay, and then this is 36 out of 52. This is 12 out of 52. And you notice it's converting into decimals for us. That's okay. 3 divided by 52 and 1 divided by 52. Okay? So in list 1 I have my outcomes, in list 2 I have all my probabilities. So now I go into stat calc, and you're going to go to 1var stats, and in list you're going to put list 1, and in frequency list you're going to put list 2. That's just second 2. And you're going to calculate. And the mean is your expected value. So what's the expected value for playing this game? It's -$1.35. So on average you will lose $1.35 for playing this game. Now the variance, we got to show our AP people that too, so we're going to take each value, -5 minus $1.35 quantity squared times 36 out of 52 plus ... and then we're going to do 95 minus $1.35 quantity squared times 1 out of 52. Now be careful here. Notice that there's no S of x because this is not a sample. This is the standard deviation from playing this game. The standard deviation is $13.80. Do not put that for the variance because that is not what the variance is. The standard deviation is $13.80. If you put an equal sign after this and you put $13.80, you're going to get docked for it. Okay, because that's not what the variance is. This is what the standard deviation is. Okay. Now what you could do is put a square root over that whole thing and then put equals 1380, and then you would put the standard deviation there, and that would be fine. But just be careful with that. Okay. So what if they double their bets? So what's the expected value, E sub x, if we double our bets? And what's the new standard deviation if we double our bets? Well, we're multiplying by 2. So guess what? On average, you would lose twice as much. So you would lose $2.70. And your standard deviation, you would have $27.60. Now if we play the game twice, what's the expected value of x plus x? We would do -$1.35 plus a -$1.35, and we would still get the -270. But the standard deviation, we would add the variances. And then take the square root. So we do 1380 squared plus 1380 squared, and we'll take the square root of that, and you get $19.52. So when you're using the calculator, you still have to show your work. We just abbreviate it. I don't show all 4 of my calculations. I show these little dots in the middle, but that must be shown. If you just throw these values down on your paper without showing your work, it's not a complete response, and that would be so on my test as well. Okay, so you still must show your work. Alright, so let's look at this last problem. Suppose a car dealer here, he has 2 processes that he does. And he does a mechanical checkup, and then he does a appearance prep. The mechanical checkup costs $50 per hour, takes an average of 90 minutes, a standard deviation of 15 minutes. The appearance prep costs $6 per hour, takes an average of 60 minutes and a standard deviation of 6 minutes. So what are the mean and standard deviation of the total cost and time of repairing the car? State any assumptions that are necessary. Well, since we have two different events, and we're going to be adding these together, we must be assuming that they are independent. So the mean time of the appearance plus the mechanical, let's see, the appearance takes an average of 60 minutes and the mechanical takes an average of 90, so it's 150 minutes. And the standard deviation is 6 squared plus 15 squared. So we added the variances, and we then do those on the calculator. So that's 6 squared plus 15 squared, and we get 16.2 minutes. Was the probability it will take longer to do appearance than the mechanical? Okay, well, as it stands now, if I do appearance minus mechanical, I would do 60 minus 90, and I would get negative 30. So the appearance on average takes 30 minutes less. The standard deviation, I would still add the variances. I get 6 squared plus 15 squared, and I get 16.2 minutes. So we're assuming that these are independent, and we're also going to assume that they are normally distributed. So the mean here is negative 30. Now appearance would take more than mechanical if I went up to 0 and I shaded that way, right? So what we're going to do is the lower bound is going to be 0. We'll make the upper bound 100. The mean is negative 30, and the standard deviation is 16.2. And it's like 0.032, so it's going to be highly unlikely. So what are the mean and standard deviation of the total cost? So the mean for the appearance, let's see, so let's see, it costs $6 an hour and it takes an average of 60 minutes, so the mean is going to be $6 for the appearance, and the mechanical, it's $50 an hour and it takes 90 minutes, so that's an hour and a half. So 1.5 times 50 is 75. So on average it takes $81. And then to do the standard deviation, we do 6 minutes at $6 an hour. So 6 minutes is 1/10 of an hour, so 1/10 of $6 is 60 cents. And then the standard deviation here, 15 minutes, is 1/4 of an hour. So 1/4 of 50 is 12.5. And then we got to square those and add them. So we would do 0.6 squared plus 12.5 squared, and then we do $12.51 after we take the square root. Now if I do the difference in costs, I'll do mechanical minus, we would do $75 minus $6, and on average it's going to be $69. And the addition, when we do the standard deviation, we're going to add the variances. So we're going to do the exact same thing we did here. It's going to be the same $12.51, because even when we subtract independent events, that's our assumptions, independent events, in both of these, we add the variances. Okay, we always add the variance.